Okay, here we go, kiddos. This is one of our last lessons of this section, and this is absolute extrema. Um, what we're going to be doing is we're going to be doing a thing called the candidates test. And so here's what it is. All right, so you're given some function, blah, 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 blah. And you're asked to find what are all the absolute maxes and minimums, not the relative maxes and mins, but the absolute. And so they'll usually give you some sort of number line here, like from -2 to 3. What are the absolute minimums and maximums on here? All right. So the general idea is this. We are going to do a thing called the candidates test. I think I spelled that right. And so what this is we are first going to find all the critical values. Again, what a critical number is, or what a critical value is where the derivative is equal to 0 or where it's undefined. Okay, either the function or the derivative itself. Where is it undefined? Where is there just really weird stuff happening? So where's the derivative equal to 0 or undefined? All right. So say, for instance, we take this f, we take this derivative, and so the derivative comes out to be blah, 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 blah. And I have critical numbers at x is equal to -4, 0, 1, and let's say 5. Okay, a lot of critical numbers. All right, what the candidates test does is this. It's going to test all of the important numbers in the realm. So that would be the 0 and the 1. Those are the only numbers in our interval. So it tests all the critical numbers as well as the endpoints of the interval itself. So what you're going to do is you're going to plug into the original function, -2, 0, 1, and 3. Okay, so -4 and 5 were not in the interval, so they don't count. So you test all the critical numbers as well as the endpoints, the ends of the interval itself. And then again, you put that just back up into the original function. So you're just getting straight up y coordinates off of this. And so all the important pieces are found. Now let's just see what happens. And let's say that this comes out to be, this gets an answer of 5, this gets an answer of -1, this gets an answer of, let's say, -3, and this gets an answer of 0. Okay, so we test all the critical numbers as well as the endpoints. So what this is saying is this. The absolute max is the largest answer. And so that would occur at the point -2, 5. That's where the absolute maximum occurs, because 5 is the largest answer out of that. And then the absolute minimum would occur at 1, -3, because that is the smallest y coordinate. And so you pick out all these candidates, including the endpoints, and then you just kind of test them out. And that's how you find absolute maximums and minimums. Okay. So it looks like they're actually going back to optimization. I'm assuming we're going to get to the candidates test. All right, find two real numbers whose difference is 40 and whose product is a minimum. Okay, so two numbers whose difference, that's a subtraction, is 40 and whose product is a minimum. All right, so x is equal to 40 plus y. So it's time for the derivative. We're going to find the optimization of this. So negative 20 is a critical number. Go ahead, test that out. So notice how it's saying any real numbers this time. It's not saying that they have to be positive. So y of negative 20 is being tested on the product's derivative. So negative 20, oops, I don't want to test, let's go negative 30. And test that in my derivative. So 2y plus 40. So this is a negative, and I'm assuming this is going to be a positive, so above, so let's go negative 10. Same idea, positive number. This is a minimum, so product is a minimum, there you go. And so find two real numbers, so the y is equal to negative 20, and that would imply that the x would be, what, 20? Okay, again, just another optimization problem. A box with a square base and an open top is to have a volume of 4 cubic feet. Find the dimensions that are required for the least. Okay, again, so I don't know why they said absolutes. All right, so this has a square base. So these are all x's, and then they don't define what the height is, so I'm going to assume that it's different. I'll call that height y. And so the volume is base times height is 4 cubic feet, and the material used, there are the 4 sides, which are x times y plus the very bottom, which is x squared, and that is the surface area of this. All right, so let's get going. I think it'd probably be in my best interest to solve for a y. That way I don't have to do that much substitution. So let's solve for y. Y is equal to 4 divided by x squared. So 4x, this is 4 divided by x squared plus x squared. So this is what? 16 over x plus x squared. So this is what? 16 plus x to the third over x. Okay, critical number time, so we go with the derivative, and that's bottoms up, derivative of the top, minus, leave the top alone, derivative of the bottom is 1, divided by the bottom squared. Okay, so getting critical numbers, I get a critical number coming off the bottom, x can't be equal to 0, so that's a critical number, and then the top, the thing making everything equal to 0 would be x to the third is equal to 8, thus x is equal to 2. So that's another critical number, 0 and 2. obviously 2 is the important one. We're not going to take the 0 answer, but it is a critical number nonetheless. Okay, so let's go ahead and test this out. So x and the surface area is 0 and 2. So let's test the number 1 in the derivative. So that's 2x to the third minus 16. That's negative. Go with the number bigger than 2, like the number 3. That's positive. That's implying that this is a minimum. And that is what we want. We want the minimum, the least amount of material needed. That's the material needed is this area, the surface area. So the least amount of material needed is occurring when x is equal to 2. So that would imply that y is equal to 1, and the surface area is 4 times 2 times 1 plus 4, 12. All right, so these are in feet. The surface area would be square feet. I guess these are just more optimization problems. I don't know why they call it absolute extrema. But, okay. So a book is to have an area of 90 square inches. Okay. With 1-inch margins on the bottom and the sides and a 1/2-inch margin on the top. So the top is thin, and then there's 1-inch margins on the side and the bottom. So 1, 1, 1, and the top is a 1/2-inch margin. Find the dimensions of the page that will allow the largest printable area. Okay, so the area is the printable area, and that would be x minus 2 and y minus 1.5. Let's go with x. X is equal to 90 divided by y. So area is equal to 90 divided by y minus 2, y minus 3 over 2. Wow, gross numbers. All right. Let's take it from here. All right, so the first multiplication is this 90 times y, so that's just going to be 90. The next one is the 90 times y times negative 3 over 2, negative 3 over 2. So that's 90 times, in essence, 3 over 2, and that is 27 over 2. So this will be minus 27 over 2y minus 2y plus 3. So this is negative 31 over 2 y plus 93. All right. So that's just the area, though. So don't get super excited. We figured out the area. All right. Again, I feel like I'm doing something wrong, so let me just consult my answer key here real quick. Oh, I know why. I know why. I see a mistake in my math. That's why. Because you're an idiot. All right, let's back this up. Hold on. Let's try this one more time. I just, sorry. So the first one is yes, 90, but the second one is when I multiply negative 90 by negative 3 over 2, get a different answer than I did last time. It's negative 135 over y. That's what my big mistake was. And then I have negative 2y, and then I have plus 3. All right, so this is negative 2y minus 135 over y, and I'll deal with this in just a moment, plus 93. And then multiplying everything by getting a common denominator of a y, this would be negative 2y, and then I'll move the 93 in. So plus 93y minus 135. You see, this should be a y squared, all over y. There it is. Now that makes sense. Okay. All right. So derivative. Haven't taken a derivative yet. Bottoms up. Derivative. Give myself just a little bit more room here. Minus, leave the top alone. Derivative of the bottom is 1. All over the bottom squared. So this is what? Again, let me get my a little bit more room, and then I'll shrink it down. Negative 4y squared plus 93y plus 2y squared minus 93y plus 135 all over y squared. So 93y drops. This is a negative 2y squared plus 135 all over y squared. Okay, critical numbers. Critical numbers are when y is equal to 0, or can't be equal to 0, and negative 2y squared plus 135 is equal to 0. So that's going to be 135 divided by 2, square rooted. I'm just going to get a nasty number, and I'm just going to live with it. So y is equal to plus or minus, obviously plus 8.2158. Okay. I think my answer key might actually have something different, but forget. So testing this out. So I'm going to check a small number like 5 into the derivative, which is negative 2x squared plus 135 divided by x squared. Positive, bigger than 8.2, negative. So this is a maximum, so that is a maximum area. Right, so my y is equal to 8.2158, which is the square root of 135 over 2. And then x is so 90 divided by that is x. And then the maximum area of the page, 90. Inches. Okay, a metal cylindrical container with an open top. Okay, so there's no top on that. Holds 1 cubic foot of holds 1 cubic foot. So the volume is 1 cubic foot. So the area of the base times the height holds 1 cubic foot. Times the dimensions for the least amount of material. So the surface area of this is there's the bottom, which is a circle, plus the sides, which is the circumference times the height. Let's solve this for height. So this would be 1 divided by pi r squared. And so that updates our surface area here. Surface area is pi r squared plus 2 pi r h, which is pi r squared on the bottom. So some immediate simplification is pi in one of these r's. So that leaves this right-hand side to have a denominator of r. So this is going to be pi r to the third plus 2. Okay, that is the surface area. We're after the dimensions. So this is going to be the derivative bottoms up, derivative of the top, minus, leave the top alone. Derivative of the bottom is 1, all over the bottom squared. So 3 pi r to the third minus 1 pi r to the third is 2 pi r to the third. Okay. So we have our derivative. So critical numbers. Critical numbers, the bottom can't be, r can't be equal to 0. I'm sorry, this should be r squared. Sorry. That denominator should still be r squared. I don't know where r to the third came from. The top is r to the third, that's for sure. All right, and the other part of this is where is 2 pi r to the third minus 2 equal to 0? So this would be plus 2 divided by 2, so pi r to the third is equal to 1. So that means r is equal to the third root of 1 over pi. let's test that out. Let's go just a little bit smaller. Let's go 0.5 into the S prime, which is 2 pi r, which is, as I was saying, 2 pi r to the third minus 2 divided by r squared. So that's negative. And then above 0.68 is, let's go with like 0.75 or something like that. It's positive. And so that should be a minimum, which I think is what we're looking for. Find the dimensions that require the least amount of material. Yes, that is correct. So the R is 0.6828, and the height would be, so again, that was the third root of 1 divided by pi. So the height would be 1 divided by pi r squared, and which looks like the same thing.